Very good. Good catch. All right. So, first of all, from this side to this side, that has to do with just the definition of combination. So n choose k is n factorial divided by k factorial times n minus k factorial. That is by definition, and same with this one over here. So are we doing okay so far? Okay, the first line is just by definition. And then the second line is a very simple algebra trick. Instead of saying n minus in parentheses k minus 1 n parentheses, we just say that we just move things around. We move the parentheses around. So instead of saying that, we just say it is n minus k, the whole thing, plus k. Are we good with that? Okay. So from the third to the fourth line, it is multiplying the numerator and also the denominator by, um, let me see, by k itself. Okay. Now this one is tricky. This one is tricky because the numerator is simple. Okay. If I multiply n factorial by k, we just get n factorial times k. Okay, that's an easy one. The bottom or the denominator is a little bit tricky because when you multiply k to k minus 1 factorial, you get k factorial. Is that clear? You good? So let me say that one more time. K times k minus 1, the whole thing factorial, is just k factorial. We're just telescoping the whole thing. So once we have that, we move on from the third to the fourth item. So from the third to the fourth item, what we are doing is we are subtracting, not subtracting, we are dividing. We're dividing both the numerator and the denominator by n minus k, the whole thing plus 1. Okay, so on the top, on the numerator, when you subtract the numerator, which is n factorial k, when you divide it by n minus k plus 1, it's just that. Okay, there's no easy way to simplify that. But the denominator, on the other hand, when you look at n minus k, the whole thing plus 1 factorial, and you divide it by n minus k plus 1, you just have a smaller factorial. So we are just shrinking the factorial by removing one term by dividing both the numerator and the denominator by this term over here. So by the time we get to the fourth line, we can see how the two sides of the addition, they both have exactly the same denominator, which means we can combine the denominator and then just kind of work with the numerator. So the numerator, we do kind of the same trick over here. We basically look at the numerator and then we just say, okay, what if I were to multiply n factorial by 1? Except that 1 is expressed as n minus k plus 1 divided by n minus k plus 1. Is that okay? So with that, let me scroll down. Okay. There's a little bit more. So after that, we can now see, this denominator is the same over here. This denominator is also the same over here. So we just combine a whole bunch of stuff, okay? So we just merge the two addition or the two terms of addition to share the same overall denominator. And then on the numerator itself, they also share the same denominator. Are we good so far? Okay. So now we look at this term here, okay, and then we move things around a little bit. Um, so we combine the division by n minus k plus 1 to the overall um, denominator. So that becomes, just n minus k plus 1 factorial. And then for the numerator, um, it is okay, so for the numerator, we use distribution. So once we use distribution, n factorial times n plus 1 is n plus 1 factorial. And then the other side, we just kind of n factorial minus k, because we are distributing, that becomes n factorial k, but it's a subtraction. This is an addition. So these two terms cancel out. And that's why in the end, we just end up with n plus 1, the whole thing factorial, divided by k factorial times n plus 1 minus k factorial. But that is really n plus 1 choose k. Are we doing okay so far with the math? Okay, now because it's an open book and open notes exam, okay, this is going to be in the final exam. I'm not going to ask you to prove this again. Okay, so that saves you for now. Okay, but the technique used to prove this is something that can be useful when you move on to a 4-year university. So CISP 440 is the kind of capstone class, at this level, before you graduate. This is quote unquote the, you know, the class that is at the high end of the CISP classes. But guess what? A community college can only teach lower division classes from the perspective of a 4-year university, which means there's a lot of this stuff coming your way after you transfer. Okay, so if you like math, it's great news. Yes. So which two lines are we talking about? The last two? Because that is the definition of n plus 1 choose k. Okay, so let's go back and take a look at the definition of n choose k. N choose k is by definition from the previous module to be n factorial divided by n minus k, the whole thing factorial times k factorial. That is the definition. So all we are doing here is to recognize n minus 1 as one thing. So that's how we can kind of conclude that the second to the last line is really the same thing as n plus 1, the whole thing, choose k. Yep. All right. So are we good with this? All right. So this looks like, well, it looks like a bunch of mumbo jumbo. Okay. So can we double check to make sure this math actually works out? So you can do that by using, the easiest way to do this is to use a spreadsheet. So I'm going to show you how to use a spreadsheet to kind of just demonstrate and show to yourself that the math actually makes sense. All right. So we are going to have to look at the column as one and then the row as the other one in terms of n versus k. So let me go back to the equation and set up the row and the column. So I think I'm going to use the row for how many we're choosing from, and then we are going to use the column for the number of items that we choose from that many. So n would be the same thing as the row number, and then k is kind of like the column number. Okay, so we go back to the spreadsheet, and I'm not sure it's not this one. I just made one for today. I think it's this one here. Okay, first thing first, change the name 2025 1105, like so. So one little problem is, the row number starts with one, the column number also starts with one. Well, that's not too hard to fix. We just have to subtract one, all the time. Um, all right, so let's go ahead and look at those numbers. Um, I'm just trying to, think of how to express that. Okay, so I think I know how to do it. All right, so hmm, no, no, it's not that. I have to come up with the formula to do the calculation, but then I also have to quote unquote label the rows and columns correctly. So I think I know how to do this. Okay, so imagine column A is saying k equals to 0, and row 1 is saying n equals to 0. So everything is 0 oriented. Are we good with that? Okay, all right. So now it becomes combin. We are saying the number of items to choose from is the row number, but we have to remember to subtract one from it because we want it to be 0 oriented instead of 1 oriented. And then the number of items that we choose from that many is the column number. So that would be the column number, column, and we will also have to subtract one because otherwise column A is known as column 1 if we convert it to numbers. So that becomes a 1, okay? and that's also a 1. And then we expand it sideways like this. We get 1, 1. And then we expand this one down, and then expand this one, 2. Okay, not that. Ah, nope. Go away. There we go. So we choose to do it this way, and then we can expand this one down just by 1, and then we expand this one out by 1. Are you guys starting to see the pattern? It is the same as the Pascal triangle, except the triangle is it's like the Eiffel Tower. Not the Eiffel Tower, the other one. Tower, what is, huh? Pizza. Yep. Yeah, pizza. Tower of pizza. Yep. It's leaning. Okay. Because instead of having a triangle that looks like this, yep, we just kind of tilt it. Okay. So we want to kind of double check and go to maybe 5. Okay. Go to 2 more rows. So we go down by 1, and then we just go across. And then when we do this one more time, I think that's what we saw last time in class. So all we have to do is can't control the mouse cursor. There we go. All right. So are we convinced now that whatever we were talking about before is working? Because okay, let's just pick a particular number that's somewhere in the middle. Let's pick this one. Okay. So this one is representing 5 choose 2. This is 5 choose 2. So what makes it a 10? I mean, once you recognize the pattern, you say, oh, 10 is, these 2 items added to that, right? So, well, what is this? This is 4 choose 1. This is 4 choose 2. So that matches the pattern that we were talking about before, which is this pattern here. This is our row number. These are our column number. And the next row, would have this pattern. Are we doing okay so far with Pascal's identity? This is known as Pascal's identity. Are we doing okay? Yes. Okay. All right. So now we're going to prove, what is known as the binomial theorem. So binomial theorem, the proof of the binomial theorem is proven by induction. This is also going to be a very powerful proof technique, just like a proof by contradiction. Those 2 techniques of proofs are used a lot in computer science. Okay, so unless you choose a particular program in computer science to avoid the hard math classes, um, this is in your future. Okay, proof by induction, proof by contradiction, all kinds of other proof techniques. It is in your future. And I can also tell you which university has a program that allows people to avoid all the heavy duty math classes. Okay, so do you think I recommend that? No. Exactly. Okay. Because when people graduate from a program like that, they really do not have the kind of mathematical training, and without that, um, I think all the future jobs in related to computer science, will require quite a bit of thinking, reasoning, and whatnot. So even though you will not be asked to prove the binomial theorem ever, after you're hired, okay? Because it's already done. Why would your employer ask you to do something burning, their money, to do something that is already published? Of course they won't do it. You'll be asked to do something harder because this is already done. Okay, it's easy. So proof by induction. So let me start with proof by induction first. So we'll go back, we'll come back to talk about how to prove the binomial theorem by induction. But instead of doing this particular proof, I am going to show you a slightly different kind of proof. Okay, and that is going to be based on a recursive function. So let me start up mousepad so I can show you the function that I want to use. Okay, and This is not it. I'm gonna create a new document. There we go. All right, so let's go ahead and consider this particular function, which you can write, in C++, really easily. So we're gonna say unsigned, okay, unsigned f of unsigned n, and this is how it is defined. Return n question mark n times. That would be too easy. Let me do this instead. 2 times f of n minus 1, and then colon 1, semicolon. Okay, this is the function. So you go like, okay, what does it actually do? What is f of, say, 3? Okay, what do you think? What do you think is f of 3? So how do you do this? How do you perform a recursive calculation by hand? That's something that we did earlier, right? Using when we are trying to figure out the outcome of permutations and the outcome of combinations. So with this one, what you can do is to go like, okay, let's try to figure out what is f of 3. And you plug in n and you go like, okay, since 3 is not false, so we're gonna go, we'll go for the second, we'll go for, sorry, we'll go for the then expression. So f of 3 is 2 times f of 2. So now you ask the question, what is f of 2? Well, it's not f of 0, so it's going to be f of 1, 2 of f of 1. And then you ask what is f of 1? It is 2 of f of 0. And then you ask what is f of 0? Aha. So at that point, n is false, okay, or it's 0, which is considered false. So the function is going to return 1. So now you plug that 1 back into here. So that means f of 1 is really just 2. And then you plug that 2 back into here. So that means f of 2 is really just 4. And you plug that 4 back into here. That means the whole thing is just 8. So f of 3 is just 8. Is that okay? All right. So with all of you either haven't taken 430 or is currently taking 430, doing this should be fairly intuitive. Okay, you'll go all the way to the base case and then work your way back up. Okay. Which is my way of saying, if you are struggling with this, that means, you might need to catch up with either 430 or, your understanding of recursion or some content of this class. Okay, so I just want to give people plenty of warning that they might be a little bit behind, okay, so they can catch up. So the whole point is, if I tell people, they can respond to it, okay? All right. So I have a grand theory that f of n really is just 2 to the power of n. Does that make sense? Okay, seems to make sense, right? But is that a proof? This is not a proof. Okay, this is just illustrating that, yeah, well, that theory works all the way from f of 0 all the way up to f of 3. But we don't know whether it's going to work for f of 4, f of 5, and so on and so forth. So we need to have a real rigorous mathematical proof so that we know for sure once and for all that f of n really is just 2 to the power of n. Does that make sense? Okay, so now we're going to have to formulate the theorem a little bit better. Let me turn off the line numbers because I think it is a little bit more distracting than it is helpful. So the theorem in this case is to say for for n in the set of natural numbers, f of n is 2 to the power of n. That is my theorem. Okay. Are we good so far? I'm not using the mathematical symbol. The in is kind of the little e symbol. Okay. This n is supposed to be funny looking because it's the set of all natural numbers. But other than that, this captures what I want to express. Are we good so far? Okay. So now, how do we prove this? Well, as it turns out, proof by induction is really handy for something like this. So in proof by induction, there are always two distinct steps. The first one is called the base case. Okay, so the base case is to prove the theorem is true when n equals to a particular constant. In other words, choose one natural number and then you just go like, yeah, the theorem works at least for that specific natural number. So which one would you choose? You don't have to choose 0, by the way. Okay? If you like the number, say 42, you can start with 42. Okay? But then you have to do the induction in both direction, which is extra work when you don't have to. So in the case of natural number, it has a very natural end to it. Does it make sense? If it's an integer, then you don't have quote unquote a natural end because it extends infinitely on both sides. But if it's a natural number, it has a natural end, which is 0. So I think it makes sense to say, we'll start with 0. Okay, so now we want to prove the base case. So the base case is saying when n equals to 0, then f of n equals to 1, which is by definition because of this one over here, okay, by definition. But then when you plug in 2 to the power of n also equals to 1 when n equal to 0. So that's why, we can conclude that f of n equals to 2 to the power of n is true when n equals to 0. Are we good so far? So you go like, well, that is not really helpful because there's an infinite number of natural numbers. We just proved that the theorem is true when for one specific natural number. So here comes the magical step. The base case is usually really easy. You just look at the recursive definition. Whatever the base case of the definition of the recursive definition is, which is this one over here, that's what you use. So the next step is called the induction step. So the induction step also has two parts, okay? The first part is to indicate what is the assumption, okay? So basically we want to restate the induction assumption. So the induction assumption is the theorem works for all n that is less than or equal to k for some k that is a natural number. Okay, so I'm going to explain exactly what that means. The induction assumption basically says, well, we know the theorem works, but only for all the natural number n that are less than or equal to some k that is a natural number itself. Okay, then you ask, what exactly is k? I don't know, I don't care. I mean, k is just some natural number. Okay, that's an assumption. So now we have to go for the actual proof. So now we have to prove that the theorem also works, is also true, okay, is also true when n equals to k plus 1. Can it be k plus 2? No. Can it be k plus 5? No. It has to be k plus 1. Okay, it has to be the next natural step up in the sequence of numbers. Okay, so now we go like, okay, so let's see what that means. Okay. So now we want to look at f of k plus 1. Okay. So by definition, f of k plus 1, because k can be 0, but k plus 1 will still be non-zero. Okay. So that means using our earlier definition up here, that means I'm going to have to go for the recursive definition. This has to be 2 times f of k by definition. Are we buying this? Okay, are we buying this particular equality? Yes. Okay. Okay. Since I see some nods, I see some non-nods, but I don't see any heads turning. Okay, we have one head turning. Okay, so go ahead. Say again. This is equal to. This is by definition. by the definition of the function up here, because even if k, because k is a natural number, we already established that from here. So if k is a natural number, then k plus 1 is going to be non-zero, right? How can a natural number be negative? Okay, so I think we can establish this equality now. Yes? Okay. So I'll just kind of say this is by definition. Okay. But because of the induction assumption, we said that the theorem is working for all n that is less than or equal to k, which means f of k has to uh, the theorem is going to work for f of k. So that means f of k is 2 to the power of k. This is by using the induction assumption. So this is the most magical step, okay, of the entire thing. This is by induction assumption. So I'm going to pause here just to make sure that we let this sink in. Yes, because the assumption is never about k f of k plus 1. It is about f of k less than or equal to, including k. No, 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 we're still dealing with k. We are only focusing on this part, expanding to this part here. Okay, okay, let me put a vertical equal here. Are we okay? Are we comfortable with f of k is 2 to the power of k because of the induction assumption? Yes? No, no, I don't want you guys to guess. It is part of the assumption because the induction assumption says the theorem works for all n that are less than or equal to k. But if the theorem is true for all n that are less than or equal to k, that means the theorem, which is stated here, it means if you plug in k instead of n, that equality holds. That is the assumption. We good? So because of that assumption, I can look at this f of k, and then we go like, oh, okay, we can just replace it by with 2 to the power of k. We are starting out with f of k plus 1, and are we okay with f of k plus 1 being the same as this? You're not convinced. Which part is not convincing? Wait, 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 wait. Okay, we okay. Are we okay with just this part? Okay. Are we okay with okay, I'm gonna spell out. Are we okay with f of k is 2 to the power of k? Yes? Okay. So I'm just taking this f of k here and substitute it with 2 to the power of k because they are the same. So now using algebra, I go like, oh, wait, this is the same thing as 2 to the power of k plus 1. And now we're done with the entire induction step. This is the step 2, so we can just say QED. We're done. All right. I see some frowns. Okay, so tell me. Oh, so you got it? Okay. All right. What? Yeah, I established the equality. I established the equality all the way from here, f of k plus 1 to 2 to the power of k plus 1. So I'm done now with the induction step. And once you're done with the induction step, we're done. Okay. All right. So this is magical, right? Because it looks like we are not really done yet. All we have done is to say that using the assumption that the theorem works for all n that are less than or equal to k for some k in n. Um, using that assumption, we can now prove that the case of n equals to k plus 1 also works. So it sounds like we are building the proof on something that is shaky using an assumption. But the assumption is not really just an assumption. The assumption basically says, well, what about 0? Can k be 0? Yeah, because we just proved the base case. So it's not building on, the assumption itself is sound. Is that okay? Hmm? It's based on it's based on the definition of the function itself. So are we doing okay so far? Yes, go ahead. Are you referring to this? Yeah, yes. So I have to make use of one, the definition of the function itself, two, the induction assumption. So combining both of those, I can now use algebra to derive the solution of f of k plus 1 is really the same thing as 2 to the power of k plus 1, which means I have now just proven that when n equals to k plus 1, the theorem still holds. Is that okay? Okay, so let me explain this in a analogy. Okay, when I do that, most people just remember the analogy and forget about the actual essence of the analogy. Okay, so suppose that you are stranded on an island. Okay, and a cruise ship, just kind of anchored next to your island. You go like, well, I wish I could walk to the uh, from the island to the cruise ship. Okay, so I can enjoy the buffet on the cruise ship, even though you didn't pay for it. Okay, so that's what you want to do. You're starting from the island. You're standing on the island. You're safe. You're not drowning. Is that okay? So now, so that's your base case. You are standing on solid ground. You're safe. That's your base case. So the next question is, what is your induction step? So the induction step in this case is to say that, well, assume that there's a sea turtle that is always one step ahead of you, and you can step on the sea turtle, and you'll be safe. Okay, and then the proof by induction, the induction step is basically saying if you are standing on something solid, you can always count on a sea turtle swimming right in front of you within a safe step distance. That is the induction assumption. Okay. And then the proof in the induction step is basically saying, well, since it's within a safe distance from one step, you can always step from whatever you're standing on onto the back of a sea turtle and be safe again. Are we doing okay? So using, hmm, say again, on something safe, not necessarily solid. So we are assuming the back of a sea turtle is perfectly safe. You're not going to fall over and drown. Is that okay? And I know I'm recording myself, and someday some animal right people is going to come back to me and sue me for animal abuse or promoting animal abuse. So I'm going to say those sea turtles voluntarily to say that, yes, you can step on my back. I would like to be off surface. Okay, so that is the assumption also. Yes. Say that one more time. No, that is not what I said. Would it be true? No. You can plug in the numbers and figure it out. You can plug in f of k, let's say k equals to 5, okay? So f of 5, according to what we know here, is 2 to the power 5, which is 32. 32. 2 to the power 5 is 32. So f of 1 is 2. 32 plus 1 is 34. It is not 64. You just have to plug in the numbers and you can find out that it doesn't work. All right. So is that analogy working a little bit? Okay. Yep. So once again, proof by induction is super important when you need to prove the correctness of algorithms. You might be asking, what algorithms are we talking about? Sorting algorithms, search algorithms, and so on. The proof of correctness of most algorithms, whether they're recursive or iterative, still depends on proof by induction. Okay, so that's a really, really powerful proof technique when it comes to computer science. All right, so that's proof by induction or the structure of proof by induction. So now that we have talked about the structure of proof by induction, do you want to see another example or is this okay? We can do one more, sure. Huh? We can do something else. We can do something that is very not obvious. Okay, so we can say, huh? Factorial is too easy. Let's do something even more fun. Okay, so this time we return if n is non-zero, it returns. Okay, I have to think about this one a little bit. No, Fibonacci has no actual quote unquote closed form, so that makes it kind of hard to make a proof out of. So this one is, I have to remember how to do this. I think, okay, it definitely involves f of n minus 1 for sure, but then I have to remember what to do with n. Okay, give me a second. I have to do some derivation on the side. Can't use that paper. That's fine. I can just hide this over here and do a little bit of math that you cannot see. Uh, okay, I think I got it. I think I got it. Plus 2 times n minus 1. Okay, erase my little hint so that you don't see the hint. There we go. All right, getting back here. All right, let's go up like that. Oh, okay. That's my bad. Colon 0 this time. Okay. So we look at this new function f. Okay, it is recursive. If n is non-zero, then we are going to calculate n of f of n minus 1 plus 2 times n minus 1. Okay, so this time I hope it's not obvious. Okay, some of you guys are pretty smart. You look at this and call like, yeah, yeah, I know exactly what that is. Okay, but if n is 0, then we just return the 0. Is that okay? All right. So I am not going to kind of give you the examples like f of 2, f of 3, and so on, and I'm going to go straight to the theorem. Okay. So the theorem in this case is for n in k, in n, sorry, in natural number as a natural number, um, f of n is n squared. That's my theorem. Okay. So now we have to prove it. So we do the proof by induction again, base case. So the base case, once again, because we're dealing with natural number, so the base case is, let's just pick n equal to 0. So once again, you don't have to do it this way, but if you don't do it this way, if you pick some random number to begin with, um, it just makes the proof, twice as long unnecessarily. Okay, so we're going to use a natural end of the range of numbers. So let's say n equals to 0. So when n equals to 0, f of n equals to 0 by the definition of n. Does that make sense? Because when you look at the definition of f, when n equals to 0, it returns the else value, which is 0. So this is by definition. Are we good? Okay. I'm going to assume it's good. What about n squared? When n is 0, n squared would also be 0. So that means I can now establish that f of n equals to n squared, but only when n equals to 0. Does that make sense? So that's my base case. So the base case is always just a single case that you have to prove. And typically, if you choose the base case of a recursion, that's the way you want to do it. Okay? So now we go like, okay, what about the induction step? The induction step has two components. The first component is called the induction assumption. And in this case, it looks exactly the same as the other one. The theorem works for all n that are less than or equal to k for some k in n. Looks the same. And then step two is almost exactly the same too, because now we start with f of k plus 1. So because k itself is a natural number, so k plus 1 has got to be non-zero, which means now we have to go with the recursive call. So the recursive call in this case is going to be f of k plus 2 times k minus 1. Is that okay? That's by definition too. This is by the definition of f itself. But because of the induction assumption, we already know that f of k is the same thing as k squared. So now we do the substitution. F of k is now k squared plus 2 times k minus 1. Hmm? Yeah, so I think I made a mistake somewhere. This doesn't. Mm, I'm looking at the math, and trying to see if that makes sense. So let's say it's 3, so that's a 9. I think, no, that doesn't make sense. Yes. Well, this is an n minus 1. Okay, you mean this plus 1? Why are we choosing the plus 1? That is the nature of proof by induction. It is basically saying the next available step. Yes. It's not exponential for sure. Okay, it's not exponential, but I think I messed up the equation itself. So let me just plug in some numbers here to see whether that makes sense. So we'll say it is a 1. Okay, so plus 2 minus 1, that is 1. So if it's a 2, then we have f of 1, which is 1. And then we have the 1 times this cancels out. So that seems to make sense. I think the parentheses, I intended the parentheses to go this way. Oh, wait. Oh yeah, you're correct. Okay, you're correct. So I did not plug in the numbers correctly. 2, yes. So in this one it would be wrong too. There we go. Okay. That makes a lot more sense. Thank you. I did not apply my own equation correctly here in the proof itself. All right. Okay. That's good. So now we do some math over here. We have k squared, okay, that nothing can touch that. And then we have 2 times k, and then we have 2, and then minus 1. The 2 minus 1 is just 1, so now we have k squared plus 2k plus 1, which we know from where? This is now k plus 1, the whole thing squared. So that's the end of the proof. So essentially the same kind of steps, except the math in this one is a little bit trickier. Tricked me, right? I forgot to plug in the k plus 1, forgot the plus 1. So any questions about this one? This is proof by induction. Okay. So are you asking, is it always, is the induction step always, going to k plus one? The answer is yes. Huh? The first line. What do you mean? Okay, let me turn on line number so you can designate the actual line. Okay, which line? Line 47? What about it? Sure. So what do you want to plug in? So f of 3 is okay. So when you plug in f of 3, we go by the definition here because 3 is non-zero. So now it is f of 2 plus 2 times 3 minus 1. Does that make sense? Yes. F of 2 is f of 1 plus 2 times 2 minus 1. Okay. And then f of 1 is f of 0 plus 2 times 1 minus 1. And then f of 0 is finally just 0 by definition. So now we go backwards. Okay. We replace this with a 0. And then we do this calculation. 0 plus 2 minus 1 is just 1. Right? And then we go back and substitute this f of 1 with a 1. So now we have 1 plus 2, excuse me, 1 plus 4 minus 1 is just 4. So this evaluates to 4. And then we plug that back to here. F of 2 itself is 4. 4 plus 6 minus 1 is 9. Okay, what do you mean by f of k plus 1? Okay, so if you're concerned about this one, then you should not be plugging in numbers because this one is based on the definition of f. There's no need to plug in numbers. I'm only plugging in the numbers to show you, how the first four parameters would work out. Yes, 51. Yes, the equality holds all the way. So every line, the equality of every line is correct. On which line? On line 54. Yeah, I don't understand why you want to plug in numbers here. Okay, if k plus 1 is 3, if k plus 1 is 3, then this k plus 1 will also be 3. I'm not sure what you mean by plugging. Okay, I'm not sure what you are trying to plug in because you cannot plug in k equal to 3 at one part and plug in k equals to 4 in a different part. The plugging in works only when you're dealing with the definition, but in the proof itself, it doesn't help you because we have already established using the induction assumption that the theorem is true for all n that are less than or equal to k. Okay, okay, all right. We did a substitution right here. So this is where the substitution happens based on the based on the induction assumption, we know that f of k is k squared because that is what the theorem says. Why would we? This is a recognition. The recognition is k squared plus 2k plus 1 is also known as k plus 1 squared. Say that one more time. Leave it here? No, because it is not in the same form as this. So f of n equals to n squared. Whatever you put inside the parentheses as the argument to f, that thing squared, we should establish that equality. So if you stop one step short in this form here, that would not complete the proof. You have to put it into this particular form because you have to show whatever is in the parentheses in the call to f is that thing squared equals to f of whatever is in the parentheses. Huh? We are trying to use this technique on the binomial theorem. No, Pascal's triangle is done already. If you want to understand Pascal's triangle, Pascal's identity is all you need. We only use Pascal's identity to come up with this triangle. That is all based on Pascal's identity. Because what we can see is this 4 plus this 6 equals to this 10. This 6 plus this 4 is this 10 over here. What would I 50 to 51? Okay, let's check that out. So it's algebra. It is, yeah, this is algebra because we recognize the coefficient is 1 to 1 and it matches, the yeah. I mean, it looks a little bit awkward, when we don't have, the square like in a superscript, but it really is the same thing as, x plus x squared plus 2x plus 1 is x plus 1, the whole thing squared. Yep. All right. Are we still doing okay? Yes. So in this class, algebra trumps calculus. We don't need no stinking calculus in this class. But algebra, on the other hand, is super duper important in this class. Okay, so are we convinced about the technique called proof by induction? No, it works whenever you have a theorem that says, for a certain range of value, um, you know, this particular equality holds for all the values within that range. So it works every time we do something like this. In same, well, that depends on how f is defined. Yep. Okay, go ahead. I'm not sure what that means. Okay, but we never. I'm not adding f of k to f of 1. It's the. I think you're still okay. So let me see if I understand. I think you're still asking about f of k plus f of 1. Is that what you're still asking? Okay, but did you give it the definition of f? No, no, no. But this is a different one. Did you give it this particular function f? Because if it was working in the assumption of the previous f, then the algebra would not have worked out this way. All right, so okay, so let's cheat together. Okay, so it is not fair if you guys can use ChatGPT. I'm gonna use it too. Okay, it's only fair, man. Okay, so I'm gonna use Gemini. Okay, so this is um, ChatGPT versus Gemini. All right, so we're gonna start a new chat. Okay, and we are going to say assume, assume, and then we'll go ahead and copy and paste. Okay, copy, switch back the following function definition. This is C code, so I give it a block C block here. Okay. All right. Then I'm gonna say use proof by induction to show that f of n equals to n squared for all natural number n. Okay. So I'm not really sure whether it can do this or not, because it's not in mathematical equation, but I think it probably understands how to do it. So we'll see. Because you have to make sure that the steps of proof and the definition of f are consistent. Okay, well, looks like it got it. Okay. So here's a proof by induction. Um, if n equals to 0, the function returns a 0, which is n, n squared, right? If n is greater than 0, the function returns f of n minus 1 plus 2n minus 1. So for the function, so the function f of n is defined like this. This is the proposal. P of n is the predicate that f of n equals to n squared for all natural numbers n is greater than or equal to 0. The base case is, when n equals to 0, the left-hand side is f of 0 is 0 by definition. The right-hand side is n squared equals to 0 squared because n equals to 0, which is 0. So that means the left-hand side and the right-hand side are the same, so the base case holds. Okay, so we got that. The induction hypothesis, okay, which is the what I call the assumption, but some people call it the hypothesis. So assume P of k is true for some arbitrary natural number k that is greater than or equal to 0. That means we can assume blah, blah, blah. Okay. And then all the steps, it's basically identical to what we just said. It doesn't work because we have a counter example of how it does not work. Okay. So let me be more clear about what I said. Okay. So what you said is f of k plus f of 1 equals to f of k plus 1. That is what you said, right? So all we have to do is to plug in a particular k where this does not work out. I'm going to choose 3. Okay. So f of 3 plus f of 1, according to what we know, is, this is 9 plus 1, right? Does that equal to f of 4, which is 16? The answer is no. If there's one counterexample showing that f of k plus f of 1 does not equal to f of k plus 1, then I'm done. I'm not sure what am I capturing what you are proposing? Okay. Alrighty. So are we so far doing good with this? Okay. All right. So now we're going to look at the binomial theorem. So we'll go take a look. Where's my slide? There we go. Okay, so the binomial theorem is, using proof by induction, is to show that for all n that are natural numbers, p plus q to the power of n is the sigma or the summation of n choose I times p to the power of I times q to the power of n minus I. So this one is a little bit more complex. Okay, so we kind of have to kind of focus on this a little bit. P plus q to the power of 0 is 1, okay, which you can re-express as p to the power of 0 times q to the power of 0, which you can also re-express as 0 choose 0 times p to the power of 0 times q to the power of 0, which you can then re-express as the summation or the sigma of I going from 0 to 0 of 0 choose I times p to the power of I times q to the power of 0 minus I, because they're all zeros, okay? Is that okay? So this is the proof of the base case. For the induction step, we are making the assumption or hypothesis that p plus q to the power of some k, we don't know what that k is, it's just a natural number, equals to blah, 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 which is according to the theorem itself, okay, except we replace the n with a particular k. So now we have to prove, that also works for the case when n equals to k plus 1. So now we start with p plus q to the power of k plus 1, which is rewritten as p plus q, one thing, times p plus q times to the power of k. But because of the induction hypothesis or assumption, we can now rewrite p plus q to the power of k into this form over here. And then going through a whole bunch of math here, we just arrive to the conclusion like this, where it is matching the hypothesis. So do you guys want me to go through the intermediate steps? No. Why not? It is algebra, okay? This is not too much, okay? I think we should go over the math because if we cannot go through this math here, I am truly worried about you, okay? I cannot lie about this. I cannot just say, you guys are gonna be fine. I'll just give you a good grade. Just move on out of here. Don't come back and ask for a better grade. Okay? That would not be good. Okay? That is not how I do things. So I have to say, if the math in this proof is challenging, we have to do something about it. All right. So the okay, so first step to the second step has to do with the induction hypothesis. The second step to the third step is simply moving the p plus q over here into the inside of whatever we are summing, okay? Because p plus q does not depend on I, so we can do it outside or we can do it inside. So once we move it inside, we split again, except, on one side we have p, multiplied to this thing here, and then on the other side we have q multiplied to this whole thing here. So on one side, the power of p is I plus 1 instead of just I. On the other side, instead of q to the power of k minus I, it is q to the power of k minus I plus 1. So is that okay? Okay. So now we go from here to here. So that is when we peel off one item out of the sigma and go like, okay, I'm going to put you over here and then do the same thing over here. So now we look at the two sigma. So you just have to identify the components that are the same and look for differences. Okay, that's basically what we do a lot when we are programming. We look for similarity. So we can see the way P and Q are set up and also the power, how they depend on I. This is the same as this one here. The difference is the sigma. This particular sigma goes from 0 to k. This one only goes from 0 to k minus 1. So what about the k choose 0 thing? Well, that is pulled out of here into here. Because when I equals to, oh, actually it's all the way to the end. I'll explain. Yes. So when I equals to k, that becomes k choose k, p to the power of k plus 1 times q to the power of k minus k, which is 0. So this part matches. But then what happened to the k choose k? Why do I change k choose k to k plus 1 choose k plus 1? Are they the same? So what is k choose k. Plugging into the equation here. What happens when I replace the n with k? No, it is 1. Uh-huh. Yep. So that is 1. So what do you think is k plus 1? Choose k plus 1. That is also 1. Okay. So that explains why I, instead of using k choose k times p to the power of k plus 1 q to the power of 0, I just say k plus 1 choose k plus 1 is also 1. We'll just use it that way. Okay. So the other thing is kind of similar. I look at this particular sigma here, and I peel off one item out of it too. Except this time I peel off when I equal to 0, and I put it all the way here. So imagine when I equal to 0, this would be k choose 0, p to the power of 0 times q to the power of k plus 1. Ah, we get the correct power combination of power over here, except k choose 0 is now becoming k plus 1 choose 0. So what do you think is k choose 0? Okay, you replace this k with, and this k, all of those with zeros. Okay, and what do we get? We get 1 again. Yep, and we have seen this already. Like at the very beginning of this class, we saw this, except it doesn't look like it, because when you look at this, what is this column representing? This column is representing k choose 0. And then the diagonal line, okay, which I'm going to highlight, this diagonal line is representing k choose k. So visually, we have seen it, okay? It's just that when we looked at this diagram or this spreadsheet, I did not identify the diagonal line versus the edge line over here. They are representing n choose 0 and n choose n. They're basically, they all boil down to 0. So given that is the case, okay, we go back here. So given that is the case, I can rewrite this expression, this one here, into this expression over here. So from this line to this line, what did I change? So the way I changed it is to change the telescoping. So instead of going from 0 to k minus 1, I is now going from 1 to k. So the number of items that we're adding is still the same. However, because we really want to start with k choose 0 over here, and if I is starting from 1, that's an easy fix. We just have to subtract 1 from I, subtract 1 from every instance of I, and then we get back k choose 0 for the first term and so on. So I'm adjusting the range of the sigma by adjusting the actual term that we are summing together. So I have to adjust both at the same time so that I actually end up summing exactly the same terms. So I do the same trick over here, and I don't think I need to do it that way. Yeah, so this one is not doesn't need that. So from here to here, I'm identifying that this sigma goes, the I of this particular sigma goes from 1 to k, and the same with this sigma over here. So that makes it possible to combine the two sigmas into one single sigma, and then we just say that, okay, these terms go here, these terms go here. But we also have one more thing in common between these two. If you look at the powers of P and Q and the powers of P and Q with respect to I, they are identical. So that's how we can combine these two into here. It is basically factoring instead of distribution. It's the reverse of distribution. So once we have that, okay, then we identify, hey, this looks like something that we saw earlier in class. It is Pascal's identity. So by using Pascal's identity, I can combine these two terms or this particular sum into k plus 1 choose I. And now we go like, oh, well, in that case, um, this term is really the same thing as this term here with I equal to 0. This term over here is the same thing as this term when I equals to k plus 1, well, let's make one big happy family and we are done. So the individual steps, does require a little bit of thinking, but it is not difficult to the point that you cannot understand. Okay, so you have to put some effort into it to find out, okay, what was changed between the lines and how does it work? Are we doing okay so far? Okay, but the end result is basically saying we can start with this and then we end with this. And that's the end of the induction step. Because now we have proven that the theorem is also true when n equals to k plus 1. Except, the only difference between this one and all the both of the earlier examples is the math involved in this one is a little bit more involved. It's a little bit, it takes a little bit, it takes a little bit more explanation compared to the two examples that were easier. Are we still doing okay? All right. So we are almost running out of time, just, not quite yet. Okay, we still have about a minute. So now the question is, okay, so how is this possibly useful to me? Well, it is useful because what if the coin um, is not even? What if the chances of landing on the head and the chances of landing on the tail are different? So you go like, yeah, but we are not enforcing, gambling rules and all kinds of stuff like that. So why would that concern me? Because what we see as landing on the head can also be a bit transmitting correctly. What we see as a tail can be seen as a bit transmitted incorrectly. So now, if you know the distribution of a bit, being received correctly versus being received incorrectly, you can then calculate the chances of a packet in networking being received correctly. And you guys are going like, but this is a CISP class, not a CISN class. Why do I care about that? Because when you're playing League of Legends, you really do not want your lag time to increase. So if the packets are being dropped because somebody decided, you know what, my coffee is getting cold, I'm going to turn on the microwave, and you have an older computer that only has a 2.4 gigahertz Wi-Fi connection, that's going to kill your game. So you want to be able to model that. It's like, okay, if somebody turned on the microwave, the correct bit reception versus incorrect is going to change to this ratio. So I can basically predetermine and go like, okay, I'm gonna forfeit this game. There's no way I can win because the retransmission of the packet is gonna kill the game. My lag time is gonna go to seconds, like multiple seconds. So forget about it unless you play Heimerdinger, right? Then you'll still be fine because you just set up the turrets. It just kind of go like, yep, I'm just sitting here. My teammates will protect me. I'll be fine. Nobody plays Heimerdinger because they nerfed him so badly. When it was at the beginning, it is great because he could even heal, the towers. Did you guys know that the Heimerdinger can heal or cure or fix the towers? He just has to stay within the tower for long enough, and the damaged tower can repair. And he doesn't have a limit of only 3 turrets either initially. They nerfed him. Yep. Darn it. Hmm. Yes. So if you want to get into quantum computing, you want to learn not only linear algebra, but you also want to learn linear algebra with complex numbers. Yep. Yep. Yeah, it's called tensor, Tensor, tensor math. That's basically linear algebra. Yeah, they have they have a lot of constructs that do not exist in normal algebra. So when each element of the vector is a complex number, things change quite dramatically. There are a lot of new notations and new concepts that you have to learn. But you are correct. Linear algebra with complex number is the foundational math of quantum computing. Yep. Yeah. All right.